All right. Okay. Good afternoon, guys. Thank you for coming to the talk. I know it's after lunch, so I'll try to keep up the momentum. All right. My name is Anto Joseph. I come from India. My hometown is Kerala. So before I start with the presentation, I would like to play a small video of my hometown. We have a security conference happening in India. It's called NALCON. Some of you guys might have heard of it. The CFP is open. We pay for the travel, submit, and hopefully I'll see you there.
The most fascinating water world on Earth, the Great Backwaters, Kerala.
So I'm going to talk about bug hunting using symbolic virtual machines. Can I have a quick raise of hands? How many guys have done something about symbolic virtual machines or symbolic execution? Okay, we have 2 guys, and they are some of the authors of some of the STP solvers that I use in this talk, so kudos to them. All right. I work at the Intel Corporation, and I've been a speaker and trainer at these conferences. I'm interested in doing machine learning and some program analysis. All right. We are talking about symbolic execution and also conclick execution. Symbolic execution basically means that you are executing the program not in a concrete fashion, but using just variables. So let's assume that there is an input to a program which is like an integer, probably something like 5 or 6 or something. Instead of executing the program with 5 or 6, you execute it with a variable, and you come up with an expression, a mathematical expression, which would possibly lead to one of the results. So that is like the simplest explanation of symbolic execution. Conclick execution combines symbolic execution with dynamic program invocation, basically running the program as well as doing this variable-based symbolic execution. And why do we need to talk about this? So have you been to DEF CON this year? There was a competition called the Cyber Grand Challenge. So if you see, it was about autonomous computers trying to find weaknesses in software and trying to generate exploits for such weaknesses. And it was completely autonomous. One of the teams, which was on the top 3, open sourced their implementation, which is called Anger. The team's name is Shellfish. And I was very curious about how these things work, and I started to look into it. And they have a very active Slack channel, so if you have any doubts, you can always pop in and ask them what is happening and all that. So I highly recommend checking them out. And basically, I will have a slide right here. So consider this as a very simple C program. And you are trying to fuzz this particular C program. Are you familiar with the concept of fuzzing? Right. So fuzzing basically means you try to give the program arbitrary input and try to see if you can hit a vulnerability, like if the program crashes or it does something abnormal which is not really supposed to do. So if I try to compile this program and try to fuzz it with a dumb fuzzer which doesn't understand how a program works, it just tries to do some sort of mutations on the input that I give it and tries to try to exercise many code paths. But as you can see, there is an if statement, which means the vulnerability is only hit if the variable A is 1, 2, 3, 4. Do you think a regular fuzzer would be able to accurately generate that particular input so that you can reach the vulnerability condition there? So you can spend all your time bit flipping or using random mutators to reach a vulnerable endpoint. But then if you have a simple check like this, which is usually something like a file magic, so if you are fuzzing a file processing code, every file mostly has some sort of a magic at the beginning of the file. And if you basically mutate that, I think most of the file programs will just ignore the file because it's just consider it as invalid. This is one of the simplest checks a program can employ. So in software security, when we want to fuzz, we need to reach or we need to exercise the maximum code paths possible. How do we do that? How can we make the fuzzers intelligent? So what we did at my work was basically try to incorporate symbolic execution with fuzzers so that whenever the fuzzer is stuck or can't really exercise many more code paths, or the health of the fuzzer is not that great, it will try to use the symbolic execution engine to try and reach more code paths, and then it will give that feedback back to the fuzzer so that the fuzzer is able to trace more code paths. So a public implementation of one of the fuzzers which uses this technique is open sourced by the Shellfish team called Driller. The paper about Driller is online, so you can always check it out. It's one of the papers which describes how they incorporated AFL, which is one of the very popular fuzzers, with the symbolic execution engine. So whenever AFL has less interesting paths to explore, they basically try to use their symbolic execution engine to feed different paths, interesting paths into the fuzzer so that the fuzzer can reach more inputs. So symbolic execution is very useful. We have seen it providing good results in some of the CTF competitions and some of the software verification challenges. I will have some links to some of the blog posts which uses symbolic execution in a real-world fashion, so you can always check it out. Okay, so the very basics of symbolic execution relies on the satisfiability modulo theories. So if you are interested in reading the theory, I have linked it. It in itself is like another presentation, so I'm not going to talk about it. The language used by the SMT solvers is called the SMT libs language, and the standard is defined over there. So SMT solvers are basically the extension of the Boolean satisfiability solvers. So it basically checks if a formula can be Boolean can be satisfied in Boolean. All right. And these are some of the SMT solvers which are popular. Z3 is from Microsoft Research. It's a high-performance theorem prover, and you can always grab it from the GitHub link. STP is used with CLI, which is one of the symbolic virtual machines that we use in this talk. The guys who have wrote is like right there, so you can always say hi to them. It's a really cool theorem prover, so we will use that in our CLI demos. And all right, let's do a Z3 demo. Okay, so As you can see, I am trying to solve a very simple expression, which is basically x is greater than 2, y is less than 10. And so you basically give the theorem prover some conditions and ask for the result, which will satisfy this particular condition. So I will be like Python example1.py, and it gives me an input. So y equal to 0 and x equal to 7 actually satisfies that condition. So this is a very simple use. Now, what about okay? So we are basically checking if this particular condition can be solved. Can it be sat solved? So that is the first print check, and then it checks what is the result. So as you can see, it's another example, just another example. So you can see that it is sat solvable, and those are the results. Now you can also use sat solvers to simplify your equations. So if you have a complex equation, which we'll come into in a moment, you can see that it tries to simplify these expressions. And once you simplify it, you can basically ask the sat solver to solve it. So let's see how it does. So it solves these expressions into these 3 lines. So when you symbolically execute a program, you will come up with let's assume that there is a program which adds 2 numbers, a and b. So when you execute the program, the result would be a plus b, right? And in a complex program, there will be much larger variable space, and you will have to solve that particular equation to get what is the result. So I will explain that visually. So this is basically how it would look like when you symbolically execute a program. So you read an input, and I would consider the input as a, which is just a variable. And then I reach the next line in the source code, which basically says add 5 to the input. So basically, the equation becomes x is a plus 5. Because a is the first input. We consider a as the input. Then we hit an if condition. From the if condition, the program has basically 2 paths. One is to the left and one is to the right. And then we read another input, and then we basically fork until we reach an error condition or an end condition. So this is basically how it looks when you symbolically execute a program. And to reach any of the end nodes, there will be a specific path. So this program might have 4, 5, 6, 7 paths. All right? To reach the end states, it will take different number of paths. And we keep a list of all these paths. And this path has to be given into a SAT solver. And then once you solve it, you will have the result. What is an input that will let you get to the first end condition or the third end condition. And for this purpose, we are using CLI. It is available from GitHub under these licenses. It is built on top of the LLVM compiler. So we basically need to have a LLVM compiler set up and all that. Or you could basically just Docker everything. They also provide a Docker container which is ready to go. So I will basically use that for my demo. So this is a very simple C program. Can you tell me how many outputs how many code paths does this program can take? This is basically a simple program that is right there on the CLI website. So how many paths does this program have? We are all hackers. We should be able to figure that out. How many possible paths does this program can take? 3. tree. All right, let's verify that. And here, I am calling this program with a concrete argument 1. Instead of 1, we have to symbolize that particular variable. So it would look like, okay, let me clear that. This. So instead of calling this particular function using a concrete variable, I use a symbolic variable, and to use it, you basically use this particular statement in CLI called the CLI underscore make underscore symbolic. It takes 3 arguments, and you basically call it. Okay, so you basically use clength, and then you will be presented with a bitcode file, which is the simple underscore symbolize.bc, and you use CLI on the bitcode file. And yes, we have a total of 3 paths, and 3 tests were generated. So when the good thing about CLI is it automatically generates the test cases to exercise these 3 code paths for you. So let's look at it. So I just exported the library path, and I will compile it. And I used GCC to compile it. Now we should have an a.out file. And to run one of the CLI's test files, so all the test files that are generated by running CLI will be in this directory. So actually let's take a look at what's inside that. So we have three files right here: the test001, test02, and 03. These files are binary files. To read them, we use this tool that is provided with CLI, which is the ktest file. Test, and you exercise it to the program, and you run it. Now you can just check what's the return variable, and you saw that the first program exited with 0. Okay. Now we'll exercise it with the second, and it exited with 1, and okay, the third one, and exited with 255. So 0, 1, and 255 were the inputs that is generated by CLI, and these 3 inputs actually exercise all possible branches in that program. So can you think of ways in which this could be really useful in software security? So if you have a really large C program and you want to exercise all the paths, would you use it? Would you use a symbolic execution program, or would you use a fuzzer, which would lead to like executing all the code paths? I think this, right? Okay, so let's do a much more complex demo, which would be interesting. So the other C program was very simple. So here, this is one of the really cool blog posts that I found, which uses CLI. So basically, you are trying to solve a maze using this symbolic execution program. So the code for the maze is around here. So it's like around 100 lines maybe. So you can always try to like manually audit it and see if there are any bugs and stuff like that. So I'm just gonna compile it and see if I get lucky. Maze.c. Okay, so you can basically use the arrow keys to move around this maze. So I guess it is SSS to go forward and A to maybe take a turn and see how it goes. well, AO step. So you can always try to like figure out what is it using this, and you can always do code audits. But then let's do it the easier way, which is basically using a symbolic execution engine to tell you if there is a path which is possible. So this is the modified C program. The only modification that is made is to include CLI, the header file for CLI, and I basically want to be in the winning condition, right? So when you win, it basically prints you win. So you put an CLI assert statement there so that CLI knows which code path it needs to like trace. Like CLI needs to know where you want to go, right? So you basically tell CLI using CLI assert statements which part of the program that you wanna reach. And then you basically compile it. So we would use clang again. Okay. I knew this would happen, so I have backup. Yes. So yeah, this is the bitcode file right there. So LLVM bitcode file. So you would run CLI on it. So CLI runs the bitcode file, and it will be done in like another 2 seconds, I guess. Okay, and it has generated around 306 test cases. All right. So what the assert statement does is it makes the program to fail. So in the CLI directory, we have to basically check what is the test case that has failed. Okay, so the test case that errored out is the test case number 140. So we just want to know what input caused the error. So basically, what input resulted in executing the win statement. To do that, we use the ktest tool, which is the tool that you use to read the CLI test files, and you give it the path, which is ktest, and this is the input. Okay. So let's run it and see if it works. Wow. So it can basically go through walls. Who would have thought of that? So the proposed solution is something else. So the actual solution is a bit longer. This is the right way to go, but then we just figured out that there are fake walls. So how do you figure out what is the actual solution? Because CLI only gave one error. So what CLI does is, once it tries to generate the first possible execution path, it stops. So you can give it another argument which basically says keep going until you figure out all possible paths. And once you do, you can come up with various test cases. Basically, this is one of that. So this one just goes crazy. Yeah, it's more polite. Yeah. So as you can see, some of the solutions are right there. So this source code is available in the Please tutorial directory. I recommend all of you to just go download Docker and then it's like a couple of 4 or 5 commands, and you can just start playing with it. I also have a CTF. How many of you play CTFs here? All right. Okay. So something that's kind of useful for CTFs maybe. So there is a CTF file called the stage2.bin. It's here. So it's a L64, and you can. So let's see if we can figure out what this program does. Wow. Let's use the visual option. I think visual option is always better. Yeah. So I loaded the same binary in IDA Pro. So you can see that this is how it looks. And the main function basically has this sort of a call graph, right? Okay. So you definitely don't want to be here. This is like a fail condition. Try again, right? So I want to end up at the success condition. So what's the easiest way to get like some C code out of it? So what you could do is like you can use the Hexrace plugin. So you basically go here and then generate pseudocode, and it gives you almost compilable C code. It doesn't work all the time, but then when it works, you can basically translate this source code to something that you can manipulate, play around. So let's see how that can be done. So the same, I have the source code here. It's basically what we saw in IDA, but I have added the CLI header file again, and yes, I need to reach the good condition, right? So I basically added the CLI assert statement there, and let's execute this. And also defs.h file, which is basically available from the IDA's directory. So you basically add it over here. Okay, you use CLang, you generate the bit code, which is right over here. Then you use CLI. So let's actually run the binary and see how it works. So it asks for a pass that you have to provide. So I'll just give it jargon. No way, I'm getting through that. So the argument that I have to symbolize, like we symbolized the variable a in the first demo, we want to symbolize the the command line argument that we are providing. So CLI provides a way to do that. So these are some of the arguments that you can provide to CLI so that you can symbolize it. So over here, I will do this. Okay, so we basically gave it the argument, but this time my command line argument has a lot many things going on. So let's take it apart and see what it is about. Okay, so this was my command line argument. Okay, so basically we are specifying a version of libc that CLI can work with. So when you create C programs, you basically use libc functions to make things easier for the developer. So when CLI has to exercise the code paths, CLI has to understand what it is doing, right? So the CLI developers have provided the version of libc that we can use to test our programs. So which is called the UC libc and a POSIX runtime. So things like the write, read, such system calls are supported by this runtime. So, and I just made this argument some 100 bytes because I don't really know what is the length. Okay, and I executed it, and we have some of the CLI test results here. Now let's see what failed. So, okay, the first argument failed. Okay. Okay, we have a fail condition, so let's read. What's that condition? To nan dot. Wow. Oh yeah, sorry. Thank you. Right, so it says Pandy Panda. Let's just see if it works. Yeah. Just goes ahead and prints the key. So this is basically solving CTFs without actually reverse engineering it. So here you go. So right now we have the source code. And in most CTFs, you don't necessarily have the source code. So what do we do about it? We can use this tool called Anger, which can basically work with function offset. So you can basically give it what offset do you need to reach. So let's actually look into how to do that. We have this binary here. So this is a very simple crack me. I don't have the source code for it. It's called the AIS3 crack me. And let's look at, I'll do the analysis, go to visual mode, go to the main function. So this is the flow graph, all right? And without any reverse engineering, we can basically say that I want to be at this offset. I don't want to go there because it says he's sorry. But here it says this is the correct key. So I definitely want to be at 4000602. Okay. So you basically take note of that offset. So we know what the offset is. Now we go into Anchor, demo 1. Let's execute AIS3 and I give it a jargon key. It says it's sorry. Now let's look at the Python file. So basically in Anger, you load everything as a project. We load the binary here. We basically try to, this is the only line that you need to bother about, which is basically asking Anger to try and find this particular offset, which is basically where the key is, all right? I don't have anything else. I just know the offset, and then I do the Python sol.py and wait, and hopefully let's see if it prints out the key. Right. Okay. Seems like this is the key. Let's take a look. Yep, that's a secret key. So without reverse engineering, just by looking at the offsets, you ask the symbolic execution program to try and figure out a path which will lead you here. And by solving that specific path, you figure out an input that will get you to that specific path, and then you solve a CTF. So this is all really cool, but can we do all of this within IDA? All right. So this is IDA, and I will load a CTF key right here. Sorry, a CTF binary right here. And it looks like this. This is the main function. Okay. And as you can imagine, I need to be at the win condition. So what can I do about it? So first, let me just execute that binary. Because it's a Windows binary, I use the Win32 debugger. I say yes, so it does the execution. Now let me execute it with an argument because the binary takes an argument like this. So basically the binary name and an argument. So I'll give it an argument name of A's, some A's, and I use this utility called pounds, which is a IDA plugin, which helps you do symbolic execution using Triton within IDA. So Triton is a symbolic execution framework, which is by Quarks Lab, I think. So this is the config menu of pounds. So basically, I ask pounds to use the symbolic execution engine and symbolize the argument, which is the command line argument. You hit OK, then you run it. And as you can see in the logs, it basically has symbolically executed the program. The Triton is the name of the symbolic framework that we are using. So it has executed on this particular binary, and it has colored our graph. So let's look at why it did it and how it's helpful. So you can see that IDA's disassembly view is now colored. I will basically look at the graph, and it says that the symbolized registers is EAX, and the memory over here is symbolized, and this is the jump condition, which basically lets you either win or lose. So let's right-click on it, use SMT. SMT solve formula, do this, and I come up with a solution right here. So basically, putting that with the binary gives you a win condition. So you can come up with any number of solutions, and this is one of the ways in which you can basically come up with a solution just within IDA, and you can basically ask the symbolic execution engine what could be the possible input that I could use to reach a specific input. Now, when you run it on really large binaries, if you want to explore the whole binary, you must understand that there is a condition called path explosion, because huge binaries can be like really come up with a number of paths, and the SAT solver may not be able to solve all of it, and it will take forever. So I recommend running the SAT solvers on specific offsets of the binary rather than the whole program as such, so that you can target the symbolic execution to a specific part of the program rather than the whole program itself. Okay, so some of the questions were, how do we prevent against someone solving our product key logic or something like that? There is a paper that discusses some countermeasures, which is basically code obfuscation, which uses the tainted variables. It's not just adding jargon to the whole program, because SAT solvers can basically identify, or the symbolic execution frameworks can basically identify dead code, and they'll just eliminate it. They won't even bother to execute it. So that doesn't work. But if some of your obfuscation code actually relies on the input that is being symbolized, then that conditions and using multiple loops and arrays and stuff actually has a huge impact on symbolic execution engine. So you could basically look into that. You can read that paper. It's good. And this is basically what I spoke about anger. And these are the components of it. The pounds is basically the IDA plugin that I used within IDA to solve it. It won the IDA plugin contest last year, I think. So it's really nice. And thank you.